Okay, next, uh, we were talking about the the inner product. I mean inner product, but we use the matrix to help us to find the inner product. Okay, so we uh we denote the dot is the Euclidean inner product on Rn, and we define the function u and v is the au dot av. Okay, so show that this function is an inner product on Rn. Okay, what does it mean? It means that so for example, if we scope on R2, okay, and we let a vector A is a 1, 2, minus 3, and 4, like this, okay, and you need, and the matrix A is an invertible matrix, so it's easy to show that this matrix is invertible. Okay, then if we need to find uh, the inner product of u and v when u is the 1 2 and v is the 0 4, then we need to calculate a multiplied by u, so this one is 5, right, and this one is a 5. And AV, what is the AV? AV is 1, 2, minus 3 and 4. 0 multiplied by 0, 4 here. And this one is 8 and 16. Okay, so the inner product of u and v that divided by the above is a vector 5 5 dot with the 8 16. So this one is the 40 plus 80, right? This one is 120, like this. Okay, we need to show that this function is an inner product on Rn. Okay, so this one is quite easy, it's not hard. Why? Because we know that the dot, this one, we know that the dot, this one is the inner product, so we will use the property of the inner product. Okay, so that's why we fix an invertible matrix of order in A, and we let vector u, v, and w to be Rn, and k is the scalar. And then for number 1, u the inner product of u and v is, this one is au dot av, and we know that this one, the dot product is the inner product, right? Because we already proved it, so that's why we can swap. Okay, so for number 1 easy, number 1, number 2, number 3 is easy. Okay, and for number 4, part 1, you can see that the inner product of u and u is au dot au, right? But for this one, it's greater than or equal to 0, because we already showed that the dot product is the inner product, right? And for the other part, we need to prove that if u inner product with u is equal to 0, then u is 0. So from this one, we know that u dot au is equal to 0, right? And from this one, because we know that this dot, the dot function, this one is the inner product, so that's why we can conclude that a multiplied by u is the 0 vector, right? And from this one, because a is invertible, so we can, so this imply that the vector u is the zero vector too. Okay, so this one is not hard. Okay, so that's why we can conclude that this function is an inner product on Rn. Okay, and you can see that this one is also the inner product, right? So in this space, or I mean in this function, I mean this inner product, we call this inner product is the matrix inner product, or sometimes we say that this one is inner product on Rn generated by the matrix A. Okay, and from this one, so we can as we talk with you before, we can see that the dot product in Rn, I mean the dot product, the usual dot product, this one is the AU transpose multiplied by AV, right? And from this one, for the property of the transpose, is the A transpose, is U transpose multiplied with A transpose and multiplied with A multiplied with A, V, like this. Okay, so I think this one is not special. Okay. Okay, next, if you need to copy this page, so please pause it. Okay, we will move to the next slide. Okay, actually I think the next slide, so I need you to do it by yourself. Okay, so to show that the weighted Euclidean inner product are special cases of matrix inner product. Okay, what does it mean? It means that the weighted Euclidean inner product is also is the matrix inner product. Okay, what does it mean? So if you need to read the solution, so please pause this page. Okay, so what does it mean? It means that you need to show that if we define the weighted Euclidean inner product like this, so you need to show that there exists an invertible matrix A such that this inner product is equal to AU dot with AV. Okay, where dot is the inner product, I mean where dot is the Euclidean inner product. Okay, so this one is not this one is I think this one we can do this one as the exercise. Okay, so please do it by yourself. Okay, it's not hard. And if you need to compare your solution and my solution, so please pause it. Okay, next we move to the author vector space. Okay, and now we will move to Rn to be the set, or to be the sum object that has a many dimension. That is the matrix. Okay, we define the function u and v is the trace of a u transpose and v. What is a trace? The trace is the sum of the diagonal entries of A. So I think all of you already know trace from teacher Gui's lecture, right? So we will use the property of the trace to prove that this function is the inner product on the set of the matrix. I mean of the set of the square matrix. Okay, which the entry are real. Okay, so before we show this, so I need to recall that the trace of the matrix has four property like this. Okay, for number one, the trace can be the trace of A and A plus B is equal to trace A plus trace B. And for number two, trace of Ka equal to K could multiply with the trace A, where K is the scalar. And number 3, the trace of A transpose is equal to trace A. And for number 4, trace of A multiplied by B is equal to trace of B multiplied by A. Okay, so for the following properties, so I will not I will not prove to you, okay, because all of you knows know this property, and I think all of you need to prove this property by yourself. Okay. For number 1, we need to prove that the inner product of u and v is equal to v and u. Okay, so this one is the trace of u transpose and v, right? And from this one, we know that we will use the property of the transpose of the matrix, that u transpose of v u transpose v is equal to u transpose multiplied by v transpose, right? And from this one, we use the property of the transpose, that this term is equal to the transpose of v transpose and multiplied by u. Okay, that's why we obtain we obtain the second line here. Okay, and next we can conclude that the trace of the transpose of v transpose u is equal to the trace of the v transpose u because of the number 3. Okay, and from this one is the definition of the inner product of b and u. And for number 2 is, I think it's not hard because we need to find the inner product of u plus v and w. And what is the inner product of u plus v and w? Is the trace of the transpose of the matrix u and v, right? U plus v transpose multiplied by the matrix w. And from this, and the next step is we obtain from the property of the transpose, the u plus v, the transpose of u plus v is a u transpose plus v transpose. Okay, and next we distribute the bill from the right hand side, and next we will use the property of the trace, that the trace of the sum matrix is the sum of the trace. Okay, this came from number 1, and the first term is the inner product of u and v, and the second term is the inner product of v and w. Okay, and for number 3 is quite easy. I think you can see. I think you can do it by yourself. Okay, if you need to copy this page, so please pause it before we will move to the number 4, because the number 4 is quite tedious. Okay, we will move to number 4. For number 4, we cannot use the four properties of trace. Okay, so that's why we will take u to be the matrix like this. Okay, the matrix that has the entry u11, u12, blah blah blah, like this. Okay, and if you have a matrix u, so you can find a u transpose like this, right? And the next step is you will find the product of the u transpose and u. Okay, and for this one, you can see that if we need to find the element of the u transpose and u in the first entry, I mean the entry 11. So this one is equal to u11 square plus u21 square blah 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 to un1 square, right? Why? Because if we find this one, right, this one came from the first right? The first row of the U transpose and the first row, and the first column of U, right? And so because we need to find only the trace is the sum of the diagonal entries of A. So that's why, I only calculate the diagonal entries of this matrix. Okay. And for the next entry is this one. The next entry is a 212 u22 square like this, because it came from the second row of U transpose and the second column of U. Okay. And for the last one, I mean for the last entry, for the entry in N, that I label by green color. So this one is came from the row n of the U transpose and the n column. No, the column n of U. Okay. Okay. So we can find the trace of U transpose multiplied by U, right? And what is this one? So the trace is the first term plus the second term, blah blah, to the last term here. And this one, you can see that if you see the index, we run the index with 1 1 2 1 to the n1. For the second one is the 1 2 to the n2, and for the last one is n1 2 1 to the nn. What does it mean? It means that the trace of this matrix is the sum of a square of each entry, right? And this one is greater than or equal to 0 because each component is square. Okay. And next, for the equality part, so u multiply u in the product with u equal to 0 if and only if this term is equal to 0, right? And because this is the sum of the square, so we can conclude that each term is equal to 0. And what does it mean? It means that in each entry of the matrix U are 0, and we can conclude that the vector U is the 0 matrix, like this. So that's why we can conclude that this function is the inner product on the set of the square matrix. Okay. And okay, if you need to copy this page, so please pause it. Okay. So we call this inner product on the set of the square matrix is the standard inner product on the set of the matrix. I mean the set of the square matrix. Okay. Next, we will move to the polynomial space. Okay, to move to the Pn here. Okay. For Pn, so for number one, we define the function P and Q like this. So how to define it? So for number one, we will use the coefficient of P and Q, and we multiply the coefficient of P and Q, and we will sum it. Okay, this is the inner product that we obtained from number one. So number one so the question is this function is an inner product on P1? And for number two, what about this one? So this one, the inner product of P and Q is if we have the value of x, okay, if we have the real number xi, okay, the xi is this x0 to the x1. So what does it mean? It means we have the xi n plus 1 number, okay. n plus 1 number, n plus 1 distinct real number, and we evaluate p at xi and q at xi, and we multiply it, and we sum together, and we sum together. So so the question is this function is this function an inner product on Pn? Okay, for example, for this inner product is if you pick x1 equal to 0, x2 equal to 1, and x3 equal to pi on P2. Okay, P2, what is the set of P2? The P2 is the set of the polynomial that degree less than or equal to 2, right? So the inner product of P and Q, this one is px1 q1 plus px2 q2 plus px3 q3, and this one is the p0 multiplied with q0 plus p1 multiplied with q1 and plus p pi multiplied with q pi, like this. Okay, so this is the example of this function. Okay, the question is the function in number 1 and number 2 are inner products on Pn or not. Okay, this one I think you can do it by yourself. For number 1, it's quite easy, it's not hard. Okay, but if you need to copy this page, so please pause it. Okay, so you need to do it by yourself before you open this slide. And next, for the number 2 is quite hard. It's quite hard it's quite hard to prove the properties for number 4. Why? Okay, for the property number 1, 2, and 3, I think it's quite easy because we use only the property of the algebra, the property of the sum. Okay, it's not hard. Okay, so I will not talking about it. Okay, so I will focus on number 4. Number 4 is really hard for this one. Why? For the first part, number 4 for the first part is very easy because the sum of the square is greater than or equal to 0, right? So it's not hard. But for number 2, this one is hard. Why? Because P, we need to show that the inner product of P and P is equal to 0 if P is a 0. And what does it mean, the 0 in the polynomial function? What does it mean? It means P is the 0 polynomial, and it means that Px is equal to x for all x in real number. And how to prove this? So this one, we will use the fundamental theorem of the algebra the state of this theorem is every non-zero polynomial degree n has at most n roots. Okay, so from this one, P multiply P inner product with P equal to 0 if the sum of the square is equal to 0, right? And from this one, we imply that each component, I mean each term, is equal to 0. And from this one is the Pxi equal to 0, right? And why we can conclude that Px or this polynomial is the 0 polynomial? Why? Because this one, we know that from Pxi equal to 1, what does it mean? It means that xi is a root of this polynomial, right? And we know that Pxi equal to 0 for I equal to 0 and n. What does it mean? it means that this polynomial has n plus 1 root. P has n plus 1 root. Okay. And moreover, xi are distinct. Right? What does it mean? This polynomial is the polynomial of degree n and has has a root and has the n plus 1 root that all distinct. What does it mean? It means that this polynomial is equal to 0 only. Okay, that's why we can conclude that this one is true. Okay, and we can show that this function is the inner product space on Pn. Okay. If you need to copy this page, please pause it. Okay, we will move to the next slide. So, the inner product in the previous slide we call the standard inner product on Pn, and for number 2 is the evaluation inner product on Pn, and we will call the point x1 x0 to the xn are the sample points. Okay. Okay, next we will move to the function space. Okay, what is the inner product on the function space? But before we prove this, I will give you some lemma that is very useful. Okay, this lemma is that if we have a function on the closed interval a and b, and this function is a positive function. What is a positive? Positive is mean the value of this function is greater than or equal to 0. Then the integration of the fx from a to b is equal to 0 if and only if fx is the 0 function. Okay, so I will give you this I will give this lemma to you with our proof. But if you need to prove this, okay, so I have a proof for this lemma, but I did not I did not tell about the detail. Okay, it's quite hard. Okay, so but if you need to copy this page, so please pause it. Okay, I will move to the example of the inner product of the function space. Okay, so let f and g be the function in the in C1 AB. What is C1 AB? What does it mean? It means this space is mean the set of continuous function from on the closed interval a and b, and the derivative of that function are continuous. Okay, so we define the function from the function from this space by the integration of a and b, but integration of fx gx from a and b. Okay, like this. So my question is, this function on C on the C closed interval AB and is the inner product or not? Okay, and from this one, I think it's not hard. I think to prove number 1, 2, and number 3, 1, 2, 3 is not hard, because this one is the property of the integral, right? This one is the property of the finite integral. So for the number 1, number 2, and number 3, I think it's not hard. Okay, so I will skip it, and so I need to prove the number 4 because number 4 is hard. For number 4, the first part is quite easy. Why? Because the inner product of f and f is the is the integration of the f squared dx, and this term is greater than or equal to 0 because the fx squared are positive, right? We have we have a theorem about we have theorem about the integration of the positive number. Okay, and for the second part, we know that the f the inner product of f and f equal to 0 if this integral is equal to 0, right? And why we can imply that the integrand, or I mean the f square is equal to 0. Why? Because we use we use the previous lemma, right? We know that the square of function is greater than or equal to 0, and this function is a continuous function. Why? Because f is a continuous, then the square of f is continuous, is also continuous. Okay, and that's why we can conclude that f is the zero function. So that's why we can prove it. we can prove that this function is the inner product. Okay, and this one is the inner product on the continuous function space. Okay, and if you need to copy this page, so please pause it. Okay, so I think now I think all of you know about know many example of the real inner product space, right? And next we were talking about some properties of the inner product that that all of you must know, and you can use it. Okay, so it's make you to find the inner product easily. Okay, so this one is a theorem that if we let u, v, and w be the vectors in the real inner product space and k be a scalar, then for number one is if we find the inner product of the zero vector with any vector, then the result is equal to 0. And next, for number two, so we know that if V is the vector space, so we can distribute the first term. I mean, we can separate the first term, right? And actually, we can do the property to into the second component too. Okay, and for number three, not only plus, but we can use a minus. Okay, and for number four, if we need to find the u minus v inner product of the u minus v and w, this one is equal to u minus w inner product of u and w minus inner product of v and w. And for number five, we can pull k out for the second component. Okay, not only first component. So how to prove it? So the proof is quite easy. Okay, proof is quite easy. For number one. Okay, for number one. So we know that. Okay. Oh, it's my wrong typo. So this one is equal to 0. It's not 0. It's not a 0 vector. Okay, we know that the inner product is the real number, right? So we can write the inner product of 0 and v is the 0 plus the inner product of the 0 and v, right? And from this one, the inner product of 0 and v, 0 is equal to 0 plus 0, right? I mean a 0 vector plus 0 vector. And from this one, we use we can use the property number 2. Okay, the property number 2 is the additivity axiom. Okay, and from this one, and we obtain that for the right of left hand side is the inner product of 0 and v plus the inner product of 0 and v. And from this equation, we can conclude that the inner product of 0 and v is equal to 0. It's done. And from this one, inner product of v and 0 is equal to inner product of 0 and v by symmetry axiom. Okay. And for number 2, we will use symmetry axiom. Okay. And next we use the activity axiom to separate this inner product. Okay. And we will use symmetry axiom again, and we obtained it. Okay. For number 3, we will use we use the separate the symmetry axiom. Okay, one time, and for second one, and for number 2, this one we use the additivity axiom, and next from this one, the inverse, the minus of w is the minus 1 multiplied by w. Okay, multiplied by w, and this term we look minus 1 as the scalar, so that's why we can pull the scalar out. So this one is came from homogeneity axiom, and minus 1 multiplied with a plus. So this one is a minus. Okay, and we use the symmetry axiom again. For number 4, we use number 3. Okay, it's not hard. And for number 5, we use the symmetry axiom again. Okay, we use the symmetry axiom, and next we will use the homogeneity axiom, and we will use the symmetry axiom again to obtain this property. So if we need to copy this space, so please pause it. Okay. Next, from this example, okay, so we have some example here. So please express this term, express the u minus 2v, inner product of u minus 2v and 3u plus 4v by using the property of the inner product. So this one is very easy. So we use the property that we already proved it. Okay. So from this one, so we use the property number. So we can use the property number. Right. That is from this one. So we distribute. So we use the additivity for the second term. Okay, and we use the additivity for the first term here. So this one is very easy. Okay, and we obtain the result like this: the 3 multiplied with the 3 multiplied with the norm of u square minus 2 multiplied with the inner product of u and v minus 8 multiplied with the norm of v square. Okay. Okay, if you need to copy this space, so please pass it. And I will give you some exercise, okay, that you need to do it by yourself. Okay, so if we let a, b, c, d, and d be the real number, and u and v be the vector in the real the real inner product space, then find number 1, the inner product of u, au plus bv, and cu plus dv. For number 2, find the norm, the square of the norm of au plus v. And 3, find the square of the norm of u minus v. Okay, that's all for this clip.